All right, so alternating series, day 2. So yesterday we looked at an alternating series, right? Decided alternating series, terms alternate, decrease in magnitude, find out the limit goes to 0, we say converges by alternating series. Alternating series is a unique case insofar as you currently know how to find the sum of a geometric series. Sum of a geometric series is the first term divided by 1 minus r. And that's something that we need to know. The other thing that we know is we can use the integral test to kind of get a general idea of where we're at. The alternating series is going to be one of the only tests, really should be the only test, where I'm going to ask you to approximate what on earth that series equals and to be able to give me an acceptable range for what that, an acceptable range of values that the series could possibly equal to. And that's what we're going to talk about today with the alternating series remainder. Let's assume we have a series that converges, and if it converges, that means that there is an actual sum, right? S. Now I'm going to use a lot of letters here, so real fast, just so that we know, if I use the letter S, I am talking about an exact value. This is not kind of equal to this. This is not approximately equal to this. If I use the letter S, I am saying the sum is exactly that number. Let's say I approximate the sum. I find what would be called its partial sum, S of n. All right? This is an approximate value using n terms. And we've done some partial sum stuff before. If I say S of 10, we're talking about the partial sum of the series using the first 10 terms of that series. All right? One of the things that we learn is that we're going to have a remainder. Now this really messes with people. Remainder, this is what we're looking at there. R sub n is going to be called a remainder. By the way, remainder is also synonymous in mathematics with the word error. It does not mean we did anything wrong, okay? Error is kind of an interesting concept, and we'll talk about that a little bit later. Not something that I think is worth having in the video necessarily. If someone wants to ask about it, we'll definitely talk about it though. But if I have R of n, that's my remainder or error for S of n. So if I say R of 6, I know that I'm looking at the partial sum with 6 terms. If I say R of 10, I'm looking at the partial sum with 10 terms. All right? And it becomes an interesting thing. Basically what the alternating series remainder says is that we actually know what the remainder will be. It says that the remainder will be less than the absolute value of the first omitted or truncated term. If I tell you that I'm looking at S of 5, then the error for this problem is actually going to be less than the 6th term. If I tell you I'm looking at S of 20, the 21st term is actually, my error is less than that 21st term. And that actually turns out to be kind of a really useful thing. So let's take a look. Given a series, there's a series. Approximate the sum S of the series by using its first 4 terms. Okay. So part A says we want to approximate S. S is approximately. S is approximately what? Well, it says using the first 4 terms. So we would have negative 1 to the 1 plus 1 over 1 factorial. That would be my first term. By the way, I know that the n starts at 1 because it tells me that n starts at 1. Plus negative 1 to the 2 plus 1 over 2 factorial, plus negative 1 to the 3 plus 1 over 3 factorial, plus negative 1 to the 4 plus 1 over 4 factorial. By the way, that's really annoying, and I'm never going to write out this negative 1 to the like that ever again. So I hope that you enjoyed that. What I will normally do is I'll say this. Okay, negative 1 to the 1 plus 1, that would be a positive over 1 factorial. 1 factorial is simply 1. Because this alternates, I know my next term has to be negative. So this is 1 over 2 factorial, 2, plus the next term. Alternates, so it'll be positive. 1 over 3 factorial, 6, minus 1 over 4 factorial, 24. Which is exactly 0.625, 5/8, for those of you who are fractional people. By the way, I'm going to use 0.625 because it will make the next stage much easier. Okay, was that particularly hard? Absolutely not. And just so that you can see it, that is the same thing as S of 4. Notice that that is not, S is not the same thing as S of 4. Different things. Cool. B is where things get interesting. So S of 4 says that I know that my partial sum is 0.625. B says that I can apparently prove that 0.625 is less than 1/100th off from the real answer. First thing I need to prove before I start doing part B is I need to prove that this series actually does what? Should probably show that this decreases in magnitude, alternates, and the limit goes to, all right, does the limit go to 0? That definitely goes to 0. A of n alternates and decreases in magnitude. Therefore, converges by the alternating series test. Hopefully you know all of that. So the first thing I need to do is I need to show that I can actually use the alternating series remainder. And part of the alternating series remainder is the fact that I have a convergent alternating series. Since I have a convergent alternating series, what I can do is I can do the following thing. I'm going to use the alternating series remainder. You don't have to write this, but I like to write all the pieces for the first time I do a problem like this, and then I will never use all of the pieces ever again because it's really annoying. What I'm basically saying is that I want to show that the remainder is less than 1 over 100. So if I talk about a remainder, that's the same thing as talking about an error. And what is an error? Well, error is really just the actual sum minus my approximation. Agreed with that? I want to stop real fast because I'm going to write a whole bunch of gobbledygook and it's going to look really weird by the time we're done. So far, so good? According to the alternating series remainder, my remainder is always going to be less than the absolute value of my first truncated term. In this case, my fifth term. By the way, if you don't like the way that I wrote that, absolute value of a sub 5, you can actually write absolute value of fifth term and they will not mark you wrong on the AP test. Like I've seen people's papers. They put line fifth term. Line. Done. So you're allowed to write that. I'm just showing you how I would write it. And what is the fifth term? What is the absolute value of the fifth term? Well, the fifth term is 1 over 5 factorial. Agreed? And what is 5 factorial? 120. And what do I know about 120? You're done. My whole goal was to say this. What I have is the next term that exists is smaller than 1 over 100. That's the important part. What pieces do I usually show? I will usually write my absolute value of the error. I personally like this piece, but there's a lot of people who won't write it. And then I will show all of that. So if you minimal, I want to see error is less than the absolute value of the fifth term, which is the fifth term, which is the simplified version of the fifth term, which is definitely smaller than my anticipated value. Those are the pieces I have to see. I like to put the S minus S4 because then A5 makes sense to me. That's up to you. Questions so far? Okay. Say what? Question does not ask for it, I will not prove it. Because the question's not asking is this conditional, now I need this to be just a convergent alternating series, but I don't actually care about the conditionality. Plus, we actually can't prove whether that's conditional or not with what we have, so it's kind of a big hot mess anyways. All right, then we move on to C. And C may be my favorite question. What does C ask? Use your result to explain why S is definitely not 0.7. To be able to do that, you have to understand how you got to be able to use an error. So what I'm going to do real fast is I'm going to write something in a really weird error. Let's say I'm dealing with a chemistry problem, because I know most of you don't twitch too bad when I talk about chemistry. If I were to mention physics, I think you would all start convulsing on the ground. But let's say we're dealing with a chemistry problem, and let's say I'm dealing with molar concentrations of something. Okay? Let's and when I talk about molar I'm going to do a molar percentage off of something. Let's say something has a percentage of 46%. Okay? 46%, but there is an error. There's a possible error in your answer of 2%. So what are the possible actual percentages that exist? Yeah, 46, we would say something like it would be 46% plus or minus the 2%, or we would say 44% is less than the actual is less than 48%, right? This is what we want. In our problem, error defines a distance from what I expect something to be my actual value, right? So when I take a look at this upcoming question that I have here, basically what I want to recognize is that I know that my amount, my sum, is definitely whatever my approximate value is, plus and minus the error. Agreed? Now, I will never write this piece again. Well, what does that mean? It means basically I need to look at the fact that my sum has to be larger than the approximation minus the error, right? Because that gives me my smaller value. But it has to be bigger than the approximation minus the smaller value, but it has to be smaller than the approximation plus the error. Or in this case, S has to be less than 0.625 minus something, greater than that, but less than 0.625 plus something. What goes where that plus and minus is? 1 over 120. Some people will put 1 over 100. I know what my error is. My error is definitely smaller than 1 over 120. So my S is definitely smaller than, this is where I need my numbers, 0.617. Or my S is larger than 0.617. I keep saying smaller because I picked a smaller number. And smaller than 0.633. And what does that mean? It means that there's absolutely no way S can equal 0.7. When's the last time you've used this many inequalities and equal signs inside of a math problem? Geometry. Without showing algebraic steps ever. Okay. Questions at this stage? If there's no questions on this, flip the page over. Let's look at another problem. I actually forgot this problem existed for 5th period, so 5th period didn't get this one, although they got to see a problem kind of like it. This is one of the favorites of the AP test. How many terms are needed to approximate the sum of the series from 1 to infinity of negative 1 to the n plus 1 over n to the 4th, so that the estimate differs from the actual sum by less than 1/1000th? Justify your answer. Well, so what am I trying to do? I'm trying to estimate S. Agreed? Sure, that sounds right. I like estimating things. Right? So when I look at this problem, I want to figure out how many terms I need in order to do that, but I want my actual sum or my error, I want the difference from the actual sum or my error to be less than 1 over 1000. Agreed? So let's start finding some terms. What's the first term going to be? And actually, before I get too far into this, first thing I should probably do is show that, can I use the alternating series remainder? Yeah, we should probably do that since that's a condition. Conditions are good. Conditions are important. Don't skip conditions. All right, here we go. So alternating, we do the first term. You said it was 1. I agree with that. Next term. (1/16) plus 1 over, oh golly, 9 times 9, 81. That's not bad. Minus 1 over 64, 128, 256. Plus 5 to the 4th. 625. Minus. All right, smarties. Yeah, and this is where you use your calculator. Should be. Okay, what do I notice? This is smaller than the 1/1000th. And what do we know about alternating series error? Look at the question. The question is, how many terms do I need to approximate the sum so that the estimate differs from the actual sum, right? I found a number that is less than 1 over 1000, so how many terms did I need for this? Well, how many terms are in the sum that fits this? 5. There are 5 terms needed for the absolute value of the error to be less than 1 over 1000th since absolute value of A of 6 is equal to, and I just wrote this as best I could. I could have probably said 5 terms needed since the 6th term absolute value of the 6th term is 1 over 1296, which is less than 1 over 1000th, which would be perfectly reasonable. But you get a couple different ways to attack the question. These are some of their favorite questions because they're not necessarily hard. They're fairly simple questions, but if you don't know your calculus, you ain't going to get it right. Questions? All right. ladies and gentlemen, there is a 14-question assignment that's attached to this. The first 5 questions, I believe, are alternating series questions similar to the 2 we've just looked at, followed by 6 through 13, which are, does this converge or diverge? By the way, any section that asks, does this converge or diverge, is a free-for-all. You can use whatever test you need to prove that. All right. Kick butt.